Section 4.4, Indeterminate Forms and L'Hopital's Rule. If the limit of the quotient f of x over g of x as x approaches a approaches 0 over 0 or infinity over infinity, then we say that that is an indeterminate form. So we are now giving a name to some quotients that we actually saw before. We saw some limits that had 0 over 0 before when we first learned about limits. Now we're calling those an indeterminate form. We saw them back in chapter 2, but now after learning about derivatives, we get a new way to evaluate some of them. So this is called L'Hopital's rule. So the way that you pronounce this, L'Hopital's rule. Suppose f and g are differentiable and g prime of x is not equal to 0 on an open interval capital I that contains a, except possibly at a. Suppose that also the limit of f of x as x approaches a is equal to 0, and also the limit of g of x as x approaches a is equal to 0. Or suppose that the limit of f of x as x approaches a is plus or minus infinity, and also the limit of g of x as x approaches a is plus or minus infinity. Then, under that condition, the limit of the quotient f of x over g of x as x approaches a is exactly the same as the limit of f prime of x divided by g prime of x as x approaches a. If the limit on the right exists or is plus or minus infinity, then we have our answer. So this is all under that condition. As long as the limit holds, or if it's plus or minus infinity, we're able to say that. If the limit doesn't exist, that probably means that you can't use L'Hopital's rule for that particular limit. So this rule seems to only work for quotients because that's how it starts off, with a quotient, but using a little bit of manipulation, it can be applied to products by using division by the reciprocal. It can apply to differences by using a common denominator and therefore getting a quotient. And it can also apply to exponents by using logarithm rules. For an intuitive understanding as to why this works, you can think about what the derivative tells you. It tells you the direction in which the function is heading. We just came from a section that talked about that. We can think of increasing, decreasing, and concavity as well. So when you take the derivative of the parts of a quotient, you are essentially comparing the tangent lines of the two functions. Whichever one is greater, meaning maybe has a steeper slope, in the long run that will dominate the quotient. So it'll either drive you to infinity, it'll drive you to a value, or it might drive the whole thing down to 0. And we're going to see that in a few examples. So let's start with this first example. Find the limit as x approaches infinity of the quotient x plus x squared divided by 1 minus 2x squared. So here, if we think of what happens when we plug in infinity, we essentially just get infinity over infinity. So this is the infinity over infinity form. So we're going to use L'Hopital's rule. And you might think, well, we saw stuff like that back in chapter 2, and didn't we divide by the highest power? Or you could even think of how this might relate to a horizontal asymptote in pre-calculus. Yes, those things are all true. The conclusion that we're going to get is just going to agree with that. As a first example, just to let you know, this is nothing different than what we saw before, just a new way of doing that same thing. So this limit is going to be equal to the limit as x approaches infinity of, now I need to take the derivative with respect to x of the numerator. And then divide by the derivative with respect to x of the denominator. Notice this is not the quotient rule. This is just taking the derivative of the top and then taking the derivative of the bottom. That's it. So now this becomes the limit as x approaches infinity of 1 plus 2x divided by, that'll be 0, and then minus 4x. So I get 1 plus 2x divided by negative 4x. If I was to plug in infinity here, notice I would still get infinity over infinity. Actually, now I would get a negative. So let's do this again. Take the derivative of the numerator and denominator. If you have an indeterminate form, you can keep doing this. So 1 plus 2x, I'll take the derivative of that, and then divide by the derivative of negative 4x. So now when I do that, I get the limit as x approaches infinity of, in the numerator I'll have 2, and in the denominator I'll have negative 4. That just becomes 2 over negative 4, which is negative 1/2. If you go back to what you learned in pre-calculus for finding a horizontal asymptote, you would have been told to just take the quotient of the leading coefficients, meaning the numbers in front of the highest powers. So 1 divided by negative 2. And that's exactly what we got. So now, according to what we would have done in pre-calculus and in chapter 2, this is not necessarily a shorter way of doing that. But now we're going to start looking at some examples where maybe it is shorter, or maybe we wouldn't have been able to do some of those earlier processes. So our next example. Find the limit as x approaches negative infinity of x times the natural log of 1 minus 1 over x. So notice this is a product. So I had a suggestion earlier that said if you have a product, rewrite that involving a quotient. So like the limit as x approaches negative infinity of x divided by, and it wouldn't be x divided by the natural log of 1 minus 1 over x. I have to take the reciprocal of that. So that would be 1 over the natural log of 1 minus 1 over x. If you want to think about what form this is, if you plug in negative infinity, 1 over x here, that just goes to 0. The natural log of 1 is 0. 1 over 0 is the same thing as infinity. So this is really the same thing as positive infinity, or I should say negative infinity on top, divided by positive infinity. So this is another indeterminate form. So let's use L'Hopital's rule. I'm going to say that this limit is now equal to the limit as x approaches negative infinity. And I have to take the derivative of the numerator, so the derivative with respect to x of x, divided by the derivative with respect to x of the natural log of 1 minus 1 over x. This becomes the limit as x approaches negative infinity. The derivative of x is just 1. Then what I have in the denominator, I have to use the chain rule. The derivative of a natural log function means I'm just going to have 1 divided by whatever was inside. And then I have to multiply by the derivative of what was inside. The derivative of 1 is 0. And then the derivative of 1 over x is negative 1 over x squared. So this turns into plus 1 over x squared. So then simplifying what I have, limit as x approaches negative infinity. I still have just 1 in the numerator, but I've got 1 plus x squared divided by 1 minus 1 over x in the denominator. And I should simplify that. This is now starting to get pretty complicated. I've got a complex fraction because I have this fraction 1 over x squared divided by 1 minus 1 over x in the denominator. Let's go ahead and just reciprocate that. This turns into 1 minus 1 over x divided by 1 over x squared. And again, I can simplify even further because dividing by 1 over x squared, that's the same thing as just multiplying my numerator, 1 minus 1 over x, by the reciprocal of 1 over x squared, which is x squared over 1. So now when I distribute, I get x squared minus x. And again, you might look at this and say, well, isn't that an indeterminate form, or we can't really tell because it looks like infinity minus infinity? I would say just remember we've seen something like this before in chapter 2, but also this is just a polynomial. This is a quadratic function that opens up. And as x is approaching negative infinity, it means x is going to the left. What's the function as x is going to the left? It's just increasing without bound. So the answer for this is really just infinity. And yes, you could say that that means that the limit doesn't exist, but as we saw with thinking of limits later on in the chapter about limits, something like this is an important concept to remember. It does help us think of end behavior of functions. So this actually tells us that all the way back at the beginning, this function, x times the natural log of 1 minus 1 over x, it doesn't have a graph of a polynomial, but on its left side, it's continuing upwards without bound. All right, so here's another example, this time involving a difference. Find the limit as x approaches 0 of cosecant x minus cotangent x. If you were to plug in 0 here for x, remember that cosecant x is the same thing as 1 over sine x. So this would turn into 1 over 0, which is infinity. And the same problem happens with cotangent. So you might think that this is infinity minus infinity, and you might be tempted to say that infinity minus infinity is 0. I'm just going to go ahead and make a note here. Infinity minus infinity does not always mean 0. Right? Because there's no way that we can actually know how much infinity is. That's the whole point of infinity. So this is something that we cannot determine. It's an indeterminate form. But if it involves a difference, maybe we can think of common denominator. Since I already mentioned that cosecant x is the same thing as 1 over sine x, I'm going to start off by writing the limit as x approaches 0 of 1 over sine x. And then minus cotangent x is the same thing as cosine x over sine x. And so I can actually combine this now, and I can write the limit as x approaches 0 of 1 minus cosine x divided by sine x. And now if you were to plug in 0 here, cosine of 0 is 1, 1 minus 1 is 0. The indeterminate form that this is really 0 over 0. 0 over 0 does not mean 1. 0 over 0 does not mean 0. Again, this is an indeterminate form. You can't tell me an answer right here. So be careful about thinking of just answering and writing something down right here. However, what we can do, just going to take the derivative of the numerator and the denominator. So the derivative of the numerator, 1 minus cosine x, would be 0 and then plus sine x. And then the derivative of the denominator would be cosine x. And now this turns into the limit as x approaches 0 of sine x over cosine x. Now I can put in 0, and I get sine of 0, which is 0, divided by cosine of 0, which is 1, and now I do get 0. Okay, so it turns out this one did end up being 0, but don't think that that's always going to be true. All right, one more example. The limit as x approaches infinity of x to the power of natural log of 2 divided by 1 plus the natural log of x. So here I just want to make sure that we emphasize that the power here is a fraction. Natural log of 2 divided by 1 plus the natural log of x. So this is another example that I was talking about where you have exponents. And we want to take advantage of L'Hopital's rule, which means I'm going to have to do some manipulation. So this is going to bring back to mind the idea of logarithmic differentiation. So I'm going to say, let's let y equal x to the power of natural log of 2 divided by 1 plus natural log of x. Then, if I take the natural log of both sides, the exponent, natural log of 2 divided by 1 plus the natural log of x, becomes a coefficient for the natural log of x. And so now what we're going to do is find the limit as x approaches infinity for this expression that I've just ended up right here. And then I'm going to trace that back to what that means about the original expression. So let's consider the limit as x approaches infinity of this new expression. Natural log of 2, and I might as well just go ahead and multiply these two things, times the natural log of x divided by 1 plus the natural log of x. So now I'm going to use L'Hopital's rule, because if you were to plug in infinity for x, you'd essentially get infinity over infinity, because the natural log function increases over its whole domain. It never really stops. It increases slowly, but it's always increasing. So I'm going to take the derivative of the numerator and denominator. And with the numerator, don't forget that the natural log of 2 is just a number. So I'm just going to factor that out through the derivative process. And then all we really need is just the derivative of the natural log of x, which is 1 over x. So this turns into the limit as x approaches infinity of, this becomes the natural log of 2 times 1 over x divided by, and here the derivative of 1 plus ln x is just 1 over x. I've got a common factor in the numerator and denominator, the fraction 1 over x. So this just becomes the limit as x approaches infinity of the natural log of 2, which, again, that's just a constant. So this is the natural log of 2. So now to show you what this means, let's just connect a couple of things. As x approaches infinity, the fraction that we started off with here, natural log of 2 times natural log of x divided by 1 plus the natural log of x, that approached the natural log of 2. This is kind of like a rational expression where you have the same degree in the numerator and denominator. But that fraction that we just wrote, that's the same thing as the natural log of y. So this means the same thing as x approaches infinity. That means that the natural log of y approached the natural log of 2. Right? Because natural log of y is the same thing as that fraction. Well, if the natural log of y is approaching the natural log of 2, that means as x approaches infinity, what do you think y is approaching? It has to be the number that's inside the natural log. Y approaches 2. And then go all the way back to the beginning. What did we say that y was equal to? The original function that we were concerned with. So this means that the limit as x approaches infinity of the original expression is just 2. Limit as x approaches infinity, so in other words, as x approaches infinity, the original expression, which we called y, but it was x to the power of natural log of 2 divided by 1 plus the natural log of x, that actually approaches 2. So the answer for our limit is 2. So notice, even though we had something that was indeterminate and it was like infinity divided by infinity, or even up here in the original expression, this is the same thing as infinity to the 0 power. That seems very confusing, but we actually found out that in this case, the answer is just 2.